When people hear the word antimatter, they often imagine something almost magical, a fuel so powerful that a tiny speck could power your phone, your car, or even your entire city for years. And in a sense, that intuition isn't wrong. Antimatter really is the most energy-dense form of energy we know. When antimatter meets normal matter, they annihilate each other completely, converting 100% of their mass into energy, exactly as Einstein's famous equation, E equals mc squared, predicts. To give a sense of scale without diving into equations, a single gram of antimatter contains roughly as much energy as a large power plant produces over many years. Even a tiny fraction of that, far too small to see, can release more energy than tons of chemical fuel. That's why antimatter has such a strong grip on our imagination. Because of this, antimatter often appears in science fiction as the ultimate power source. Tiny, clean, and unimaginably powerful. So instead of asking whether we could put an antimatter battery into a smartphone, let's ask a more interesting and revealing question. What is the smallest antimatter battery we could possibly build, even in theory? To answer that, we first need to separate two very different things: the fuel itself, and the battery system required to use it. Here's the surprising part. The amount of antimatter needed to produce useful energy is incredibly small. To understand just how extreme antimatter is, imagine having only 1 gram of it. That single gram contains enough energy to power a smartphone continuously for millions of years. Even an electric car could be driven non-stop for hundreds of years on the same amount. Scale up further, and a large jet aircraft could continue flying for weeks, while a massive ship could operate for a similar amount of time. Beyond Earth, where power demands are much lower, that same gram could keep a spacecraft's systems running for decades. But the fuel is not the problem. The real challenge is keeping antimatter from touching normal matter. Antimatter cannot be stored in a container, because any contact with air, metal, or plastic causes immediate annihilation. Instead, it must be suspended using electric and magnetic fields, floating in a perfect vacuum without touching anything at all. Scientists do this today using electromagnetic traps, which require powerful magnetic fields, ultra-high vacuum systems, and often extremely low temperatures. Even when scientists store just a few individual antimatter particles, these systems are large, delicate, and easy to disrupt. They require constant power and careful control. So while the antimatter itself could fit on the head of a pin, the equipment needed to keep it alive already fills an entire room. At this point, it might sound like antimatter is simply too powerful for small devices like smartphones. So what if we scale up? Cars, airplanes, and ships consume vastly more power. Modern electric cars operate at tens of kilowatts. Aircraft engines reach the megawatt range. Large ships use power comparable to small towns. Surely antimatter would make sense there. But the answer is still no. Even for a car, the antimatter itself would be microscopic, but the containment system would still be enormous. A vehicle would need constant power just to keep its fuel from disappearing. In an accident, even a partial containment failure would release energy comparable to a powerful explosion. No transportation system could accept that level of risk. Airplanes face even stricter limits. Antimatter containment systems are heavy, delicate, and extremely sensitive to vibration and damage. In the event of a crash or system failure, the energy release would be catastrophic. Aviation safety standards simply cannot accommodate that kind of worst-case scenario. Ships may seem like the best candidate. They are large, heavy, and already carry complex power systems. But even here, antimatter fails. The containment and shielding would take up enormous space, consume power continuously, and introduce risks far greater than existing nuclear technologies, which are already safer and more practical. At this point, a natural question arises: what about space? Spacecraft don't need to worry about roads, passengers, or cities. They operate far from Earth, where extreme solutions sometimes make sense. And in fact, antimatter has been seriously studied as a potential fuel for deep space missions. In space, antimatter's incredible energy density is genuinely attractive. A tiny amount could, in theory, accelerate a spacecraft to incredible speeds or shorten interplanetary travel times dramatically. For long-duration missions, carrying less fuel mass is a major advantage. But even in space, the same problems remain. Antimatter still requires electromagnetic containment, vacuum systems, shielding, and constant power. Spacecraft are already extremely mass-constrained. Every kilogram launched into orbit is expensive. Adding room-sized containment systems and heavy radiation shielding quickly erases the advantage of antimatter's tiny fuel mass. There is also the question of failure. A containment failure in space would instantly destroy the spacecraft. There would be no emergency landing, no repair crew, and no margin for error. For crewed missions, the risk would be unacceptable. Because of this, even the most optimistic space studies treat antimatter as a very distant, theoretical possibility, not a practical near-future technology. Then there is the issue of cost. Antimatter is not something we can mine or manufacture easily. Today, antimatter is produced only in tiny amounts in particle accelerators, and the process is extraordinarily inefficient. Creating even a single nanogram of antimatter would cost an astronomical amount of money, far beyond the budget of any power system. In fact, antimatter is often described as the most expensive substance ever created. Producing just 1 gram would cost many trillions of dollars and require energy far exceeding what that gram would ever return. From an economic perspective alone, antimatter as a fuel makes no sense. So when we consider containment, safety, energy conversion, accidents, spacecraft limits, and cost together, a clear picture emerges. Antimatter is not limited by imagination. It is limited by physics, engineering, safety, and economics. The smallest antimatter battery we could realistically build would still be enormous, incredibly expensive, and dangerously complex. It would resemble a small nuclear facility, not a consumer device. It will never fit inside a smartphone, and it will never power everyday vehicles. Antimatter is not a battery of the future. It is a fascinating extreme, a reminder that the universe allows extraordinary energy, but only at a price that practical technology cannot afford.